right, students, welcome back to the third part of our lecture on interplanetary mission planning. This video should be relatively short. We're only going to cover around 6 slides, so not much there. There's the math. There's like basically one slide on complicated mathematics, and then we do some an example problem for Jupiter. So the topic here then, so in the previous lecture, we talked about insertion when you arrive at a planet. So let's see, here we go. Here's our diagram again. We've got the sun. We have, we depart from the Earth, say, we get to, let's say we're going to Jupiter. Here, we get out to Jupiter. Here's Jupiter, right? And then we have a patch point at Jupiter, and we can either insert into Jupiter orbit, which is not very typical, or we can do something called a flyby. So a flyby is, well, where you just fly by. You don't do any delta V maneuvering at all, and well, as we can see, there are certain benefits to doing a flyby that can be realized if you do it right. Now, let's see. I want to do this. So I can just click on this. Right. So here we've got. I'll just mute that for a second. Here we just have an illustration of what's possible. So the problem basically is that once you've put yourself on your Hohmann transfer out of the Earth's orbit, you don't have a whole lot of delta V budget left, right? And so there's not much maneuvering that can go on. You can't really escape the solar system with just the delta V budget that you have. And so there are ways of exploiting the gravity of these planets to do these slingshot maneuvers, which can accelerate your velocity and allow you to escape the solar system or visit the outer planets, things like that. This is a video of Voyager 1 and 2. You saw 2 trajectories there leaving. I believe this was on Nova or something like that. I forget exactly where I got this. It was a while back. In any case, this is a vision. This is the orbit of the Voyager 2 that you're seeing right now, and you can see it zooms out to both Voyager trajectories. Let's see. Go back. I can maybe rewind that a bit. Right. So let's go through that again. So here you start out leaving Earth. You go to escape velocity. And you're on this, not quite a Hohmann transfer, but fairly close to a Hohmann transfer out to Jupiter, which of course isn't going to allow you to escape the sun's sphere of influence. But what happens at Jupiter, if you can see, we start slowing down, and Jupiter here is moving faster than us. And when we pass Jupiter, we're going much faster than we were before we arrived. And in particular, Voyager 2 there made a much stronger gravity assist maneuver there. And its second gravity assist maneuver there at Saturn launched it out of the ecliptic and into interstellar space. And here we're going to, I believe that's Uranus. And here we're eventually going to get Neptune. I don't think it doesn't go to Pluto, but so you can use these gravity boost maneuvers to navigate out of the solar system or what have you. And let's see, zoom in. There we go. So that was the Voyager 1 and 2 spacecraft. This is actually a more modern spacecraft, the Cassini mission to Saturn, and so here on the left, we have our little launch, right, way over here, and get something stronger. So we have our launch. Our velocity increases. So it's actually, you launch towards Venus. So as you get towards closer to the sun, your velocity accelerates. That's not acceleration of the spacecraft. And then it does a flyby of Venus, which gives us a little delta V boost there. It goes down here, has a delta V actually negative, right? It's a negative delta V down here, which prepares it to fly by Venus again. And it gets another gravity assist boost from Venus. And then it actually flies by Earth and gets a gravity boost from Earth. Right, so actually negative delta V budget there, but by utilizing these gravity assists, you get a nice trajectory out to here to Jupiter. You get another delta V boost, and then you get to Saturn, and you do an injection, an insertion here into Saturn, just hopefully barely, not very fast at all when you arrive. So it's relatively low velocity there, and then you do a delta V maneuver. Here to put yourself into Saturn orbit, and then you're orbiting Saturn for a while and visiting the moons and so forth. So how does this work, right? So the trick is to utilize the patch points efficiently, right? So here's Jupiter. Sorry for my handwriting. That's really helpful. Jupiter, right? And as I said, once you arrive at Jupiter, you are going to be going slower than Jupiter because Jupiter is an outer planet. So when you arrive at Jupiter, if we can draw a picture of Jupiter, right? Here's Jupiter. There's some lines. There's its thing, right? You're going to arrive through the front door, right? So when you do that patch point, you're arriving this direction. Even so, your velocity is slower than that of Jupiter, right? And the rate at which you're approaching Jupiter from the left-hand side is, not delta V, sorry. Your velocity at apogee minus the velocity of Jupiter, and Jupiter's in a circular orbit, so it's moving faster than you, so this velocity is overall negative in sort of this heliocentric coordinate system. And then in the Jupiter center coordinate system, you arrive this direction. And then if you're clever about it, right, you can turn your velocity vector. Now in the Jupiter coordinate system, right, the velocity magnitude doesn't change at all, right? But then when you do the patch point again, patch back, this is heliocentric to Jupiter-centric inertial, right? And then you patch back to Jupiter-centered inertial to heliocentric inertial. Right, you get a delta V boost because, right, you add that velocity back in, that you add that Jupiter velocity back in, and now because this has changed direction, right, it's moving the same direction as Jupiter. The overall delta V is positive. So that's sort of my. Then we add velocity of Jupiter back in, so we're going much faster in that direction. So that's sort of my intuitive explanation. Now we'll get to the sort of mathematical interpretation. Right. So if we view this, right, here's again, we're going to be this example is actually Saturn, but it's okay. Right. So here's Jupiter again. This little ball there, so you can tell it's Jupiter. So in the inertial coordinates, right, here's, let's see, in the inertial coordinate system, right, there's the sun. You have Jupiter moving in at this velocity here, velocity of Jupiter. You're moving at this velocity here, velocity of apogee. And so when you arrive, when you do that patch point at Jupiter, your velocity with respect to Jupiter is velocity of Jupiter minus velocity at apogee. Now, this doesn't really work unless you do it with vectors, right? Fortunately, we don't really need to worry about three-dimensional vectors because everything's taking place in the ecliptic, mostly, for the most part. And so we can limit ourselves to two-dimensional vectors, which are a little bit easier to understand. And so we've got lots of pictures here on this slide. So the one I'm going to mainly focus on this one, but this this one's also valid. So what do these pictures represent? Right. So actually, they're going the opposite direction as the picture I've drawn. So apologize for that. But so this is the velocity of the planet, right, in the heliocentric coordinate system. So that's heliocentric inertial coordinate system. And this is the velocity of your incoming spacecraft in the heliocentric coordinate system. So I apologize, these directions are reversed, but that's what we have. And so when you do that patch point at arrival on the planet, the velocity vector with respect to the planet, right, is the difference between those two velocity vectors. So that velocity vector is v, well, they call it VSV minus VSP, but so I'll do that for right now. Oops. And right, those are vector differences. So that you take the vector difference, right, and it's just a vector connecting those two. So this is after patch, right? This is the velocity vector in the Jupiter-centric inertial coordinate system after patch. Right. So if we want to use this picture I've drawn down here, we can sort of think now in the Jupiter-centric coordinate system, right? And so the velocity of the spacecraft is coming in like that, right? V infinity I. So I mean, there are several different notations here, right? And they're all sort of equivalent. So for example, right, draw your attention to these things right here. Right. So the velocity of the planet, right, that we're talking about is this one. The initial velocity, in the heliocentric, right? So these are heliocentric inertial. This is heliocentric inertial, and the heliocentric inertial. So these vectors are all heliocentric. Right? So our relative velocity v infinity I here. Oops, I didn't mean to do that. V infinity I, right? That's the same as v I minus v planet. Right. And the idea is then, if you're doing a flyby maneuver, right? And here we are assuming that Jupiter's moving this way now. That you do a flyby maneuver, it's a hyperbolic trajectory, there's a turning angle, so you turn your trajectory a little bit. So this, the magnitude of this vector doesn't change, v infinity, but its direction does. Right. So it changes by an amount equal to the turning angle, so that's delta, right? And so you haven't gained any energy or any velocity in the Jupiter-centric coordinate system, but then when we convert back to the inertial coordinate system, the final velocity is v infinity 0 plus the velocity of Jupiter. So if we look at this diagram that we are looking at here, there we go, right? Here's your initial in the Jupiter-centric coordinate system, velocity vector. After you do your hyperbolic flyby, that's your velocity vector in the Jupiter-centric coordinate system. And then when we convert back to the Earth-centered inertial coordinate system, let's choose a different color here. Right, this is our velocity vector in the heliocentric coordinate system. Right. So we can see that our initial velocity vector in the heliocentric coordinate system, by rotating, right, this bit through the angle delta, has increased the length of that velocity vector. So increased the magnitude of our velocity in the heliocentric coordinate system. So that's also heliocentric inertial. Right. So, okay, the mathematics, how do you figure out, right, the change in absolute velocity after the two patch points? Okay, so first I put your attention to, right, this is the velocity vector in the Jupiter-centered inertial. I think we call this V infinity I in some of these slides. I think here they call it V infinity. So in this one they call it V infinity negative. Right. Right. Okay. And I don't have another picture. So, right. That's the relative velocity before the turn in the Jupiter-centric coordinate system. Now, in the Jupiter-centric coordinate system, it's a hyperbolic trajectory. We have a turning angle, right? And what does that do? Well, in the Jupiter-centric, it doesn't change the magnitude of this, this velocity vector here, but it does change its direction, right? And so this number here is the velocity in the Jupiter-centric coordinate system of the spacecraft after flyby. So I think they call it V infinity final, or V infinity 0 for some reason, or V infinity positive, I guess, for afterwards, right in here. So that's right. And both of these are in, this is in Jupiter-centered inertial, and this is also in Jupiter-centered inertial coordinates, right? So it doesn't seem like that would help us, of course, until, of course, we convert back to the heliocentric coordinate system, right? So this is, that's what this little term is here. So we take this whole thing here, and I'll just use a different color to emphasize. This term here, this blue term, right, is this term right here. Right. So, or the right-hand side we've plugged in for the right-hand side. So we've just expanded out the rotation matrix. It's the standard rotation matrix, assuming a clockwise rotation. Although in this case, it's actually counterclockwise rotation. In the pictures we have here, anyway. And then we add back in the velocity of the planet to convert to heliocentric coordinate systems. Right. So this is the patch point, so after patch. So after we've left the sphere of influence of Jupiter, back in the sphere of influence of the Sun, this is our final inertial velocity. Again, referring to these pictures here, we've got, here's the initial velocity, right, in heliocentric. We have a very weak flyby here. So in Jupiter-centric coordinate systems, we've got these two vectors. We do a little rotation in Jupiter-centric coordinates, like that. And we have a new velocity vector in heliocentric coordinate systems, which is right there. And that one's longer, right? So that's a pumping up maneuver, right? That's adding energy. Right. Conversely, and this is occasionally done, you can also decrease your energy of your orbit by going around the other side, basically, of Jupiter. So if you say you're coming in like this, let's see, what would be a good example of that? So you're coming in actually through the back door, for example, and you have some positive velocity, and you turn that around, right? That would be sort of, actually that would be the opposite. well, sorry, I deleted Jupiter. Shouldn't do that. So again, right, the directions of Jupiter have changed here. So in this case, you would be coming around like this and using Jupiter to decelerate your velocity vector. In that case, we have a incoming velocity vector here. This is Saturn, but whatever. So we've got the velocity of Saturn. We've got the incoming velocity. We go through a rotation now in the other direction, and our magnitude of our absolute velocity vector in the heliocentric coordinate system has decreased. And again, just to emphasize, these are the vectors in the Jupiter-centric, or Saturn-centric in this case. And these are in the heliocentric inertial coordinate system. Right. So you can decrease your velocity or increase it. Now, how effective are these maneuvers? That's, of course, the real question. They can be very effective, essentially. Right? So, for example, we have this, the ideal case. And, of course, the ideal case is never realizable, right? Because it assumes basically zero energy with respect to the planet you're approaching. But let's just play with it for a little bit. So assume that well, actually, I'm going to just erase all of this. So this is the ideal. So let me get the ideal case, right? The best possible case scenario. That's the case where here, let's say that's where you have sort of counter-rotating planets. Of course, that's not realistic, but let's leave that as it is. So your planet here, say Jupiter, is moving this direction, and you actually launch for somehow you manage to launch your spacecraft in this direction. Right? So Jupiter is moving at, in this case, 20 kilometers per second. That's not how fast Jupiter moves, but it's just an academic example. You are moving the opposite direction at a velocity of negative 20 kilometers per second in the heliocentric frame. Right? So I'll just emphasize these are heliocentric inertial. Right? You do a 180-degree rotation. Right? So basically, if we draw these triangles that we've been drawing here, here is, I'm going to draw them the same direction I prefer to draw them, which is this way. Here's a velocity of Jupiter. Here's velocity of you. Velocity, what are we calling that? Initial, okay. And so you rotate that about so that you add this. Your velocity with respect to Jupiter in this case is that, right? So, and they really should connect if we're going to do the triangle thing, right? So this is your VSV1, for example. Right? And now the rotation is, right, which is, in this case, 40, magnitude 40 kilometers per second. Right? And then you rotate that about an angle delta equals 180 degrees until you are there at moving in the opposite direction. So let's see, we're highlighting, what's our highlighting code? Green is for inertial, right? So this is the pivot point here, pivot point there. Yes, so we after the rotation, what we get is your so actually, sorry. Right. So in the Jupiter's, actually that's Jupiter. Sorry, I'm getting this all wrong. So in the Jupiter-centric coordinates, right, you've rotated this vector to this vector, right? And then when we add in, go back to inertial coordinate systems, right, the length of that vector is from here, which is our pivot point, and here I'll just draw a little, oh, I didn't like that. That didn't work very well. Can I draw X's here? Nope, it's not working very well. So I'll just choose a different color. So we've got our pivot point here is this point over here, and this point is this point over here. So then when we look at the inertial coordinate system, our velocity vector goes all the way over here. Right. So mathematically, how do we represent this? Right. So that's right. How do we represent this? So here we've got, let's see here. Our initial incoming velocity is 20 kilometers a second. That's this term right here. We've got the velocity of the planet, which is 20 kilometers a second. That's right there. Also comes in there. And so we find that this whole term here, and I apologize, this is a bit of a mess, right? It becomes negative 40. Here's the velocity of the planet, which is this term right here. And our rotation matrix, which is 180 degrees. So this, after we apply the rotation matrix, this negative 40 becomes a positive 40. This stays the same. And so now we can add up the two positive numbers, 40 and 60, and we get a final velocity vector of 60 kilometers per second. So our spacecraft was initially in the heliocentric coordinates moving at 20 kilometers a second, and after our flyby is moving at 60 kilometers a second. Right? So this number corresponds to this length right here. Let's see, this number corresponds to this length right here. This number corresponds to this length right here. And okay, I'm probably overusing that color. So that's this one right there, this one right there, this one right there, and before, right, we applied the rotation. That's that number right there. So essentially, we can triple our velocity by clever use of these gravity assist trajectories, and you can actually do even better if depending on the velocity of the planet, right? So if you had, like, say, for example, if the planet was moving faster than you are, then that would be more helpful, for example. So that's the mathematical slide. Now, application to that, of course, right? Covering up loose ends. How do we do that rotation, right? That rotation, the turning angle, right? Turning angle delta, right? Well, that's, can we get 180 degrees? Well, the answer is mostly no, right? because 180 degrees, that would correspond to a parabolic flyby. Right. And because you have excess energy, right, a parabolic flyby is zero energy, right? E equals 0 with respect to the planet. And since we are arriving at the planet somehow, we must have some energy with respect to the planet, so that a true parabolic flyby is never possible. Right. But how close can we get? Well, remember, we can. There's certain things we can control, and there are certain things we can't control. Right. So we can't control the energy. And it's really pointing the wrong thing. So can't control energy. And remember, energy is negative mu over 2, oops, goes in the bottom, mu over 2a. And so we can't control also the semi-major axis of the flyby. So what can we control? Well, as we learned in the previous mini lecture, we can control eccentricity through use of the targeting radius. So generally, if you have a smaller targeting radius, you decrease your targeting radius as much as possible without hitting the planet, you can increase the eccentricity. So small delta targeting radius implies eccentricities close to 1, right? And of course, 1 is parabolic. So you make your targeting radius as close as you can without hitting the planet. And I should mention that, but don't hit the planet. As in, don't enter the atmosphere. So obviously, you're going to be limited to a periaps equal to the planetary surface. Right? So given semi-major axis, right, that gets plugged in. That's fixed. This is relative velocity on approach, fixed. Actually, I think I'm using blue for fixed in general. Right? So things we can't change that, can't change the density of the planet. So the one thing that we can change is targeting radius, and that will give us some control over our eccentricity. Right? And really, actually, we want to invert this formula to figure out what's the eccentricity we can get for a given targeting radius. We'll get to that in the next slide. So here's the Jupiter flyby scenario. So the velocity, so we're doing a Hohmann transfer from Earth to Jupiter, right? So Hohmann transfer. Right. The nice thing about Hohmann transfers is that when you get there, remember you're entering through the front door, but the velocity, incoming velocity with respect to Jupiter, is precisely in line with the velocity vector of Jupiter. Right? It's going that way. I mean, in Jupiter-centric inertial, there is no velocity vector of Jupiter, but you get the idea that your velocity vector in the heliocentric coordinate system, if we're going to draw those little diagrams, right? There's velocity vector of Jupiter. There's the velocity vector of your spacecraft, right? And here's, let's see, I think which pivot points were we using? For which colors were we using for the pivot points? Blue and yellow and heliocentric. That makes sense. And blue for Jupiter, I guess. That doesn't make sense. Right. There we go. There's heliocentric, Jupiter-centric. So there is our relative velocity vector. If we can rotate that as much as possible, that's going to increase the magnitude of our final velocity vector. Right. And then in the inertial space, right, the velocity vectors will look like that, moving from there to there. Right. What was I saying? Yes. Okay. So we arrive at a Hohmann transfer, and we like Hohmann transfers because all these things are sort of line up, and it's easy to figure out the incoming velocity. It's sort of a one-dimensional problem. So we figure out what is the heliocentric velocity at arrival. That's heliocentric inertia before the patch point, right? And we figure out, right, the velocity in absolute space is 7.4 kilometers a second. The velocity of Jupiter is 13 kilometers a second, so we can fill in some numbers into my very small diagram here. I feel bad that it's so small. Maybe I'll just draw it again. Heliocentric, right? Jupiter velocity, and again I'm making it small. Jupiter velocity, that's 13. Your velocity, which is about half of that, 7. The relative velocity, now I'll just change colors briefly. Relative velocity with respect to Jupiter is now negative 5.64, right? And so just changing colors, not that color, right? So that comes from there, this comes there, and this comes there. Right. So the initial heliocentric, I'm using that for heliocentric, planet-centric, right? Relative velocities, VI, V planet, and the incoming velocity in the Jupiter-centric coordinates. The difference between those two, which is 5.6, moving in the negative direction. Yeah. So now, of course, we would like to rotate that. Right? We would like to rotate that to get some large velocity vector. So we would like rotate that like that, and get something like that, and color that right. Right. So as to increase our total magnitude in the heliocentric frame. Right. So to go from this to this. Right. Okay, so we have the relative velocity vector here, given here, for our formula. The only thing we don't have is a turning radius. So remember, A is given by the energy, right? So we can calculate that just using the E equals V squared over 2 equals negative mu over 2A, right? Solve for A. That gives us this. And now we want to figure out how close we can get, right? So the closest, of course, we can get to Jupiter is the planetary surface. So we're just assuming that we're just going to skim the planetary surface. I believe the planetary surface of Jupiter 11 Earth radii. That's about 100,000 kilometers or something like that. You don't want to get that close to Jupiter, quite honestly, but we can discuss that later. All right, so that gives us our P, periaps, and we can solve for eccentricity because, right, A is known, the radius of Jupiter is known, and so our eccentricity of our flyby could never be minimum value, can never be less than this. This is the minimum value. So remember, small eccentricity means large turning radius, as close to 1 as possible. And this is actually not that far off from 1, so that's actually fairly good. And so we plug that number here into the formula for turning angle, and we find that the maximum turning angle is 160 degrees thereabouts. Maximum turning rate. Now, of course, we want to use as large a turning angle as we possibly can in order to maximize our gravity assist. Now, okay, I'll come back to that in just a second. So now we plug this into the formula for the velocity after flyby. Right, we know all these numbers now, right? That's 158 degrees. This was, I believe, negative 5.9. And now, of course, we want to write these in vector form, negative 5.90. This is the velocity of the planet, which was, I believe, 13.0, something like that. And so we add those two numbers together. We multiply by the rotation matrix first, of course, and we get that the after flyby velocity is this number right here. So in terms of magnitude, right, so the velocity after flyby is about 19 kilometers per second. And remember, our velocity before was about 7 kilometers per second. Right, so we get a boost in velocity and energy of in heliocentric coordinates after the patch point of about a factor of 2.5. Right. Yep. So double 7 would be 14, and then we get a little extra bit in there. Right. So these the potential boost from a Jupiter flyby is enormous. Right, you're getting a huge amount of delta V out of this, 12 kilometers per second. Right. That's the best case, of course, right? In reality, right, we don't quite get that much delta V boost. And here we see this is the Voyager spacecraft, right? As it passes by Jupiter, gets a boost from Saturn, gets a boost from Uranus, gets a boost from Neptune. And we see that there is a delta V boost, and it's not trivial here, right? It's actually almost about 12 kilometers a second. Maybe I should draw this line a little bit lower, right? So delta V, right, about 11 kilometers per second. A huge delta V boost from flying by Jupiter. And I think Voyager 1 actually got even more. Right? Better. So just that delta V boost is enough to kick you out of the solar system, right? So here's the escape velocity as a function of distance for any spacecraft, and just one flyby, Hohmann transfer, then a flyby of Jupiter will allow you to leave the solar system. So any time after this first flyby, the Voyager probes were all interstellar. Right. Huge delta V boost, 12 kilometers a second, and it got a few others here. Looks like maybe, I don't know, what's that, 7, 8, maybe 8 kilometers per second. Maybe here 1.2, here about 1.5 kilometers a second for these other flybys as well. Right, so big delta V boosts. Before so this is more or less, there's one more slide, but it's just some pictures. Before I finish, right, I mean, so this is a relatively simple concept. The one thing that people tend to get sort of turned around on when doing this is because this is a two-dimensional problem now, there's scale vectors involved, people tend to get turned around on coordinate systems, right? And you see, even in my slides, I didn't get turned around. It's just they were using a different coordinate system than I was. Right, so you gotta fix your coordinate systems. In the heliocentric, which one you use, right? So heliocentric inertial, right, is the one you use for before and after, and it sort of has to line up with the Jupiter-centered inertial coordinate system. So just make sure you pick a coordinate system and stick with it. That's the important part. And it has to be a right-handed one too, so we should mention that. So if we go x, that's positive y, right? And then we draw Jupiter, right? Then in this coordinate system, velocity of Jupiter is actually negative 13, right? 0, right? If that was our coordinate system. And then if we did that, just using the right-hand rule, x, y, z, z is pointed out of the board, out of the whiteboard, up. It's pointed up. Alternatively, right, you can use, right, x, y, z. Now z is down, out of, into the board. So just make sure that you're using a coordinate system consistently, right? So that your coordinate system in Jupiter-centric lines up with your coordinate system in heliocentric. Typically, we just fix these to the planet. The real question becomes which is, so x, y, z. So the real question usually becomes, if we pick like x going this direction, for example, is this y or is this y, right? So that's usually where people get turned around. So it depends on if your z vector is up or not. And usually we take z up, and so actually in this coordinate system, if we wanted to make it, z up, we should choose that, right? So that's one coordinate system. The other one, this is also acceptable, right? But anyway, just choose a coordinate system and stick with it, right? That's all I've got to say with that. If you do that, then then express your final velocity. Note that this will be in your chosen coordinate system. So again, right now we'll just conclude with a couple movies. So this is these are the, well, there's been more interstellar probes now, but these are the sort of older ones. Voyager 1 and 2, which again launched about the same time, and Pioneer 10 and 11. Well, we'll see. All of these interstellar probes, there's never been an interstellar probe that didn't use a flyby of Jupiter that I'm aware of, right? All interstellar travel uses Jupiter. Uses Jupiter flybys. Now, if you have a fancy space elevator, that's another story, but we're not going to talk about that. It's flyby, right? That apostrophe S. It's a plural of flybys. Well, there we go. Anyway, so just a couple movies here we get to see. Right. This is the Voyager 1 probe. It only did a flyby of Jupiter and Saturn. There's the Jupiter flyby. It did a stronger Jupiter flyby than Voyager 2. And then it did a Saturn flyby, which actually pushed it out of the ecliptic. You see these lines here going up. After the Saturn flyby, it was well out of the ecliptic. So it's a little bit out of the ecliptic now. And then it does a flyby of Saturn, and it's out of the ecliptic. So this is moving faster than the Voyager 1 probe. Close that. All right, how do I close this? Oops. Right, there we go. Next, we got Voyager 2, same deal. This is a grand tour of the solar system. So it does a good flyby of Saturn, goes to Uranus, and then hits Neptune. Gets a little flyby there. And now it's out of the ecliptic. Typically, if you're going interstellar, you want to pop out of the ecliptic because there's too much stuff hanging around the ecliptic. You might interfere with your communications or what have you. It's just there's nothing much out of the ecliptic. So better to if you want to maintain communications and stuff like that, better to get out of the ecliptic. And I think it's below the ecliptic in this case. Here's the Pioneer ones, right? This is the Pioneer. It just passes by Jupiter and then it goes interstellar. That's pretty much it. Not very exciting. Pioneer 10. And it's interstellar. Boom. And here's just, you can see why the Pioneer flyby of Jupiter launched it interstellar right away, because it does a very close flyby of Jupiter. So within the sphere, the moons. Let's see if I can rewind that. Just pay attention to the minimum radius with respect to Jupiter. Let's let this go through again. So keep an eye on this number right down here. So it gets down to about 200,000 kilometers, right? Which is as close to skimming the surface of Jupiter as we're comfortable getting, I guess. Otherwise, Jupiter has lots of atmosphere. You never know what's going to happen. Right. So finalizing, here's some image credits. Finally, interplanetary mission planning. We have broke it down into 3 lectures, one on sphere of influence, one on patched conics, patching in and out of different orbits, Earth-centered, then heliocentered, and then Venus-centered or Jupiter-centered. And what you do in that last case, you either insert or you do a flyby. And we did the mechanics of how you compute the effect of flybys, if that's your goal. And then from flybys, of course, we can do a flyby of Alpha Centauri, if you like. Which should be fun. And it'll get there in, what, a few 100 million years or something like that. I don't know exactly. I haven't calculated. But in any case, that concludes our lecture on interplanetary mission planning. Next time we will be talking about spacecraft attitude dynamics. So we'll have a series of 3 lectures on that. And I look forward to seeing you there.